Welcome to this video. Today we will learn C Programming Language Overview. In this video, we will cover the basic concepts step by step, including variables, data types, operators, conditions, loops, functions, arrays, pointers, and many more important topics. Don't worry if you don't understand everything right now, this is just an overview. In the next videos, we will go topic by topic with simple explanations and many examples. Let's briefly look at our roadmap for this video. We have structured this tutorial to build your knowledge step by step. We will start with the fundamentals. What exactly is C? We'll look at its history and why it's still relevant after 50 years. Then, we will write our first program and understand the compilation process, how your text code turns into a running program. After that, we will dive into the building blocks, variables, data types, input and output, and operators. Once we have the basics, we'll learn about control flow, how to make decisions with if-else and switch statements, and how to repeat tasks using loops. Then things get interesting. We will cover arrays and strings, followed by functions to organize our code. Finally, we will tackle the most powerful and feared topics in C: pointers, structures, dynamic memory management, and file handling. We'll wrap up with a look at some advanced concepts like preprocessors and error handling. It's a packed agenda, so let's jump right in. So, what exactly is C? You might hear people call it a mid-level language. But what does that mean? Think of a computer as having layers. At the very bottom, you have the hardware, the physical circuits, and electricity. Just above that is machine code, binary zeros and ones that the hardware understands. Above that is assembly language, which is slightly readable but still very complex. And way up at the top, you have high-level languages like Python or JavaScript, which read almost like English but hide all the details of the computer. C sits right in the middle. It allows you to write readable code like a high-level language, but it also gives you direct access to memory and hardware like a low-level language. This is why C is so fast and powerful. It was developed by the legendary Dennis Ritchie at Bell Labs back in 1972. He created it to write the Unix operating system. Before C, operating systems were written in assembly, which was a nightmare to maintain. C changed everything. It provided a perfect balance of performance and portability. Today, verify this: Windows, Linux, Mac OS, Android, and even the software in your car or microwave, major parts of them are still written in C. You might be wondering, is C still used today? The answer is a resounding yes. It is everywhere. First and foremost, it is the language of operating systems. The logic that manages your computer's memory, processor, and files is written in C. It is also the king of embedded systems. Think of the microcontroller in your washing machine, the flight control system of an airplane, or the sensors in a smartwatch. These devices have limited resources, and C is efficient enough to run on them perfectly. Device drivers, the software that lets your computer talk to your mouse, keyboard, or graphics card, are almost exclusively written in C. And here is a fun fact: compilers and interpreters for other languages often use C. For example, the standard implementation of Python, CPython, is written in C. So, by learning C, you are not just learning a language, you are learning the foundation of modern computing. Before we write code, we must understand how it runs. Computers don't understand C code directly. They only understand binary machine code. So, we need a translator. This translator is called a compiler. The process happens in 4 stages. First is preprocessing. The preprocessor scans your code for lines starting with a hash symbol, bringing in necessary libraries. Second is compilation. The compiler translates your C code into assembly language. Third is assembly. The assembler takes that assembly code and converts it into pure binary object code. Finally, linking. The linker combines your object code with other libraries to create the final executable file, like a .exe on Windows. It sounds complex, but modern tools do all of this in a split second when you click build. Enough theory. Let's write some code. The tradition in programming is to start by making the computer say hello world. Let's look at the code on screen. The first line, #include stio.h, is a preprocessor command. It tells the computer to include the standard input-output library. Without this, we cannot print anything to the screen. Next, we have int main. This is the main function. Every C program must have one main function. It is the entry point where execution begins. Inside the curly braces, we write our instructions. We call the function printf. This stands for print formatted. We pass the text hello world inside quotes. Notice the semicolon at the end of the line. In C, every instruction allows end with a semicolon, just like a period at the end of a sentence. Finally, return 0. This tells the operating system that our program finished successfully. If it returned -1, it would indicate an error. Now, let's talk about variables. Programming is all about processing data. To process data, we need to store it. A variable is simply a named container in memory where we store data. In C, C is a statically typed language. This means you must tell the computer what type of data you are storing ahead of time. If you want to store a whole number, like your age, you use int, short for integer. For example, int age equals 21. If you want to store a number with a decimal point, like the price of an item or pi, you use float or double. Float is for smaller precision, double is for higher precision. If you want to store a single letter, like a grade, you use char. Ideally, char stores a single character like a or z. Choosing the right type depends on your data. Using int for a price might lose the sense, and using double for a simple count might waste memory. A program is useless if it cannot interact with the user. We need input and output, or I/O. We already saw printf for output. It prints text to the console. You can also print variables using placeholders like %d for integers. But how do we get data from the user? We use scanf. Let's look at the example. We declare an integer x. Then we ask the user to enter a number. Then we call scanf. The first argument is the format specifier, %d, meaning we expect an integer. The second argument is tricky. We write $x. The ampersand symbol means address of. We are telling scanf, go to the memory address of variable x, and store the user's input there. If you forget the ampersand, your program will likely crash because scanf won't know where to put the data. Operators are the symbols that tell the computer to perform actions. Arithmetic operators are the math basics, plus, minus, multiply, and divide. There is also the modulo operator, represented by the %sign. This gives you the remainder of a division. For example, 10 modulo 3 is 1. This is very useful for checking if a number is even or odd. Comparison operators let us compare values, equal to, double equals, not equal to, exclamation equals, greater than, less than. Logical operators let us combine conditions. Double ampersand means and, both must be true. Double pipe means or, at least one must be true. Exclamation mark means not, reverses the truth. Programs need to make decisions. Usually, code runs top to bottom, line by line. But what if we want to run some code only if a condition is true? We use if-else statements. Think of it like a fork in the road. In our example, we check if age greater than or equal to 18. If this condition is true, the computer enters the block and prints you can vote. If the condition is false, the computer skips that block and jumps to the else block, printing you cannot vote. You can also use else if to check multiple conditions in a sequence, like checking if a number is positive, negative, or 0. Sometimes you have a single variable that can have many specific values, like a menu option. Using many if-else statements can get messy. This is where the switch statement shines. Imagine a restaurant menu. You choose option 1, 2, or 3. In the code, we switch on the variable day. We define cases, case 1 prints Monday, case 2 prints Tuesday, and so on. Crucially, notice the break keyword. When a case matches, C executes the code and then keeps going down unless you tell it to break. Without break, if you picked 1, it would print Monday, and Tuesday, and Wednesday. This is called fall-through. The default case is like the else, it runs if none of the cases match. Computers are great at doing boring tasks repeatedly without complaining. We call this looping. There are 3 main types of loops in C. First, the for loop. Use this when you know exactly how many times to repeat. For example, counting from 1 to 10. You set the initialization, the condition, and the update step all in one line. Second, the while loop. Use this when you want to repeat until a condition changes. For example, are we there yet? No. Are we there yet? No. You keep checking. Third, the do while loop. This is special. It guarantees the code runs at least once before checking the condition. Loops are essential for iterating through data, as we will see next with arrays. What if you need to store the grades of 50 students? Creating 50 variables like grade 1, grade 2, grade 3 would be a nightmare. Instead, we use an array. An array is a collection of variables of the same type, stored continuously in memory. Think of it like a row of mailboxes, all numbered. In C, we declare it like int arr 5. This reserves space for 5 integers. The most important thing to remember, C uses zero-based indexing. The first element is at index 0. The second is at index 1. So if you want the third number, you ask for arr 2. Accessing an index outside the array, like arr 10, in a size 5 array, is dangerous and can crash your program. In many languages, string is a basic data type. But not in C. In C, a string is simply an array of characters. If you want to store the word hello, C stores it as H-E-L-L-O. But how does the computer know where the string ends? It uses a special invisible character called the null terminator, written as \0. So hello requires 6 spaces in memory, 5 letters plus 1 null terminator. If you forget space for the null terminator, functions like printf won't know when to stop printing and might print garbage memory until they crash. As programs get larger, writing everything in the main function becomes unmanageable. We use functions to break our code into smaller, reusable chunks. A function is like a recipe. It takes ingredients, inputs or arguments, performs a specific task, and serves a dish, returns a value. In the example, we define a function add that takes 2 integers, a and b. It returns their sum. Now, in our main program, we can simply call add 5, 3, anytime we need it. This makes code modular, easier to debug, and avoids repetition. The principle is dry, don't repeat yourself. Now we arrive at the most infamous topic in C, pointers. Many students fear pointers, but they are simple if you visualize them. Every variable lives at a specific address in your computer's memory, like a house address. A pointer is just a variable that stores another variable's address. If x is a variable with the value 10, living at address 1000, we can create a pointer p that holds the value 1000. We say p points to x. We calculate the address using the ampersand operator. We access data at that address using the asterisk or dereference operator. Pointers allow us to modify variables efficiently without copying data around. They are essential for dynamic memory and complex data structures. Arrays are great, but they can only store one type of data. Real-world objects have multiple properties. A student has a name, string, and an age, int, and a GPA, float. To group different data types together, we use a structure, or struct. Here we define struct student. Inside, we list the properties fields. Now we can create a single variable representing a student. We access the fields using the dot operator. Student1.name, student1.age. Structs are the precursors to classes in object-oriented languages like C++ and Java. Usually, when you declare an array like int arr10, the size is fixed. You cannot change it later. This is called static memory allocation, and it happens on the stack. But what if you don't know how much memory you need until the program runs? Maybe you are reading a file of unknown size. This is where dynamic memory allocation comes in. We use the function malloc, which stands for memory allocation. It asks the computer to reserve a block of memory on the heap. It returns a pointer to that block. Crucially, unlike the stack, heap memory is not automatically cleaned up. You must allow clean it up yourself using the free function. If you forget to free, your program will consume more and more memory until the system runs out. This is called a memory leak. Variables are temporary. When your program stops, the data is lost. To allow data to persist, we need file handling. C provides a library of functions to read and write files. We use fopen to open a file. We specify the file name and the mode, W for write, R for read, or A for append. We use print to write text into the file, just like printing to the console. Finally, and most importantly, we use close to close the file. Closing the file ensures all data is saved properly and releases the resource back to the operating system. We briefly mentioned the preprocessor at the start. It's a powerful tool that edits your text code before the compiler even sees it. Commands start with a hash symbol. Common uses include #include to add libraries. Another is #define. This creates macros or constants. For example, #define pi 3.14. Everywhere you write pi is your code, the preprocessor literally replaces it with 3.14. This makes code more readable and easier to change. If you want to change pi to 3.14159, you only change it in one place. In modern languages, if something goes wrong, the program throws an exception and you catch it. C is old school. It does not have exceptions. Instead, we rely on error codes. Functions typically return a specific value to indicate failure. For example, fopen returns null if it cannot open a file. As a C programmer, it is your responsibility to check these return values. We use if file == null to check for errors. We can then use functions like purr to print a human-readable error message explaining why it failed. Maybe the file didn't exist, or you didn't have permission. Ignoring error checking is the #1 cause of unstable C programs. We have covered the core of the language, but the C universe is vast. Advanced C programming gets into the heart of the machine. You have multi-threading running multiple tasks at the exact same time to use modern multi-core processors. Socket programming allows your C program to talk over the internet, building servers and clients. Signal handling lets your program respond to system events, like when a user presses Ctrl+C to stop a program. And system calls allow you to ask the operating system kernel to do heavy lifting. These are complex topics, but they are what make C the language of choice for high-performance computing. Wow! We have covered a tremendous amount of ground today. From the humble hello world to the complexity of pointers and memory management. You now have a complete eagle-eye view of the C programming language. Remember, learning to code is a marathon, not a sprint. Don't worry if you don't master every detail immediately. The best way to learn is to practice. Write code, break it, fix it, and understand why it broke. In upcoming videos, we will take each of these topics and dedicate full tutorials to them with real-world practice problems. If you found this overview helpful, please hit that like button, it really helps the channel. Subscribe and turn on notifications so you don't miss the deep dives coming next. Thank you for watching, and happy coding!